Okay. We'll do that. All right. So, when we talk about MedChem, what I want to show you is what is going to be upcoming, because the first exam is very different than the rest of the MedChem exams. So exam 2, 3, 4 and the final, and then the 5 exams next semester. In MedChem, the first exam is probably closest to biochem. So talking a lot about structures, talking a lot about like identification, some orgo stuff. You're not really going to need to do reactions. Like you're not going to be given a reactant and an arrow that has a bunch of, properties on it, and then you have to draw the product. Mostly it's going to be about, identifying products. So what kind of metabolism would this be? Or, what functional group or what heterocycle is this? When we get into the second exam, it's all drug structures. And so what I will post, and what's available to you guys as well, is my study guides from going through MedChem. And essentially what it is that you're going to learn a certain class of medications like cholinesterase inhibitors. And all of the cholinesterase inhibitors have some sort of consistent structure. So you can see that the stigmines all have this benzene ring with a nitrogen off to the left and kind of this carbamate functional group off to the right. And what you will have to be able to do is identify how these different changes to the drug will change the properties of the drug. So what you are learning right now is those fundamental changes. What is important to know for the first exam, and you should really, really, really pay very close attention to modifications of drugs. The reason why we have 30, 40, 50 drugs that all basically do the same thing is because we found some sort of chemical in nature, like atropine, and then we modified it through some sort of chemical process in the lab. And what's important to know in MedChem is what are those changes and how do they affect the molecule? Does that make sense? Hopefully. Okay. All right. So that's my little spiel. That being said, we should talk about what is on this first exam. Let me pull up the handout. I am not going to go through the heterocycles purely because that is just straight memorization. There's nothing I can really teach you with that stuff. What I would say is make flashcards, do Quizlet, but make sure you know them and don't just learn and forget, because they will be very important for the rest of the 2 semesters. All right, let's talk about ADME. So ADME is a super, super, super important process in pharmacy. It's probably one of the most talked about aspects of pharmacy. You can't have a drug without describing what happens to it. And throughout the rest of this semester, you're going to learn more and more about how the properties of the drug in each of these different processes means how drugs change and why we choose certain drugs over other drugs. That being said, let's go through and let's talk about the important parts of ADME and how that affects the drugs and how we're going to use that in this class specifically. when we talk about absorption, what is essentially going on here is that we have our lumen, which this could be the stomach, this could be the intestine. Maybe it's a inhaled drug, so this could be the alveoli. Maybe it is sublingual, so it's going through the tongue or the cheek. But essentially what is going on here is we have something that is outside the body. We have some sort of epithelial membrane. And this is not a cell membrane. This is the epithelium, which is made up of individual cells. So in order for a drug to move from the lumen, the intestine, wherever it is, into the blood, it needs to be absorbed. To do this process, it has to pass through the lipid membrane of the cells. Now, one of the fundamental things about chemistry is that like dissolves like. So for absorption, the best drugs are going to be very lipophilic. In general, we describe drugs usually by how bad they are, or in other words, how hydrophilic they are. And the rule I want you to think is that if you have an OH, SH, or NH bond, you are very, very, very hydrophilic, incredibly hydrophilic. The reason for this is that all three of these bonds cause hydrogen bonding. And we know from biochem that one of the strongest interactions in intermolecular reactions is hydrogen bonding. This is what keeps DNA together. This is how water is able to stick to itself. So a drug that has lots of OH, SH, or NH bonds is going to be incredibly hydrophilic. Now, does that mean that if you have a ketone, for example, is this hydrophilic? It's polar. So it's going to interact a little bit because we have a partially negative oxygen, partially positive carbon. But is this really hydrophilic? Not really. And so what we can categorize these types of bonds on is the dissoluting property of these hydrophilic bonds. So let's talk about what we mean there. Is this making sense so far? kind of, sort of?
Yeah.
Okay, sweet. One of the processes that actually happens before ADME, and sometimes you'll see this included, is liberation. Liberation is the process of a drug dissolving from tablet form. So if you have a pill, you swallow it, it goes into your stomach. This has to break apart into individual drug molecules. And so what we say is that this process is happening in an aqueous environment, right? Our stomach has water in it. Our intestines have water in it. Our lungs have some water in it, also known as dissolution. Yep. And so what we can measure here is that liberation requires hydrophilicity, right? Dissolution or liberation requires the drug to have a certain amount of hydrophilicity. Otherwise, it's just going to sit in your stomach like oil on water. But in the same time that we talked about earlier, it needs to have a certain amount of lipophilicity in order to be absorbed, right? Because if you have a drug that is great at dissolving into water or in the stomach acid or in the intestines, but it's so hydrophilic that it cannot cross the membrane, the epithelial membrane, then it is completely useless. So this is why we talk about two different properties, the hydrophilicity versus the lipophilicity. And you can't have 100% of one versus the other. You have to have a balance. And so this is why many drugs will have a hydrophobic region and a hydrophilic region. So for example, that's kind of small. You? Nope. There we go. So here we have the drug metoprolol. Different color. And looking at the structure of metoprolol, we should be able to identify a region that is much more hydrophobic. In other words, it's lipophilic, and a region that is hydrophilic. So we know that hydrophilic drugs, which I will put in a different color, hydrophilic drugs are those that have OH, NH, or SH bonds. So looking at the structure of metoprolol, we can say that the hydrophilic region is somewhere around here. Whereas the hydrophobic region, the part that's going to help it get across the membrane, is over here. And so we have two different regions of the drug. Now, in the packet, he gives you or in the handout, he gives you a list of how many carbons, balances, how many OH groups or NH groups. So in other words, he says that very polar groups which are our OH, NH, and technically our SH, although we don't have a lot of drugs that have SH bonds. These all dissolute, which is just a fun way of saying liberate 5 to 6 carbons. So here we have one OH bond, we have another NH bond. So we have at least 10 to 12 carbons that we are able to dissolve into the stomach. We also have weakly polar groups. And these are all ones that are heteroatoms. So in other words, these are bonds where we have CO, CN, or CS bonds. And each one of these are able to dissolute 2 to 3 carbons. Now, in the packet, he lists out all of the different kinds of groups, right? He explains them. And mostly here, he's just showing you, first of all, the name of them, because he will, point to a section of a drug and say, what functional group is this? The other kind of aspect is to be able to categorize them about very polar versus weakly polar. The goal here is to be able to say, will this drug have an easier time dissolving or absorbing? So for example, in metoprolol, we have an OH and an NH, which is good for dissolving 10 to 12 carbons. And then not counting the oxygen and the nitrogen that we've already talked about, we have another oxygen and a second oxygen, which would be 4 to 6 carbons each. So these functional groups are balancing 14 to 18 carbons. So now what we can do is we can count the number of carbons in this molecule. So there's 1, 2, 3, 9 for the benzene ring, 10, 11, 12, 13, 14, 15. So, first question first. Will this drug dissolve? Will it go from the tablet and dissolve into the stomach acid or intestinal acid? Yes. How do we know that? Because we have OH and NH groups. We have polar groups. Great, it dissolved, but will it cross the membrane into the body? Yes. Yes, it will, because the number of carbons is within this range of the number of carbons solubilized. So on the exam, you would have something like good dissolving, good absorbing, or you'd have bad dissolving, good absorbing, all that sort of stuff. So the reason why it was good at dissolving is because we contain OH, NH, or SH groups. And the reason why it's good at absorbing is because the number of carbons that can be solubilized is within this range, 14 to 18 carbons. Let's go through a different example. Yes, what's your question?
So when you got the 10 to 12 carbons, was that from just counting the amount of because there are like two oxygen. Oh no, wait, there's only one OH. How'd you get the 10 to 12 again?
5 to 6 comes from this OH and 5 to 6 comes from this NH.
Okay, so the 5 to 6 is for each, the OH, the NH, and the SH. Oh, okay, gotcha.
Right. And then this 4 to 6 is 2 to 3 from this oxygen, 2 to 3 from that oxygen.
Okay, thank you.
Good question. All right. Next up, oh, yes, what's your question?
For me, it was just more like so around the absorbing part. So if it falls in the ballpark of 14 and 18, that's good absorbing, right?
Uh,
The carbons.
it's yes, yes. Essentially. So the idea is that in order to be absorbed, you need to be as lipophilic as possible.
Yeah.
So if we could get rid of all of these oxygens and nitrogens and just have carbons, that would be perfect. The problem is that there's no way that this is going to dissolve in the stomach. So in order to balance the number of carbons, we need to have a certain number of polar atoms, if that makes sense.
Yeah. Okay.
Does that answer your question?
Yes. Yes, it does. Thank you.
Yes. Yep. The answer would be A here. Next drug we have to look at is fluoxetine. For people who don't know, this is Prozac, which this is an antidepressant. And does anybody know where the site of action of fluoxetine would be? Is it in, what do people think? Yeah, CNS, the brain, something like that. And so for drugs that need to cross the blood-brain barrier, you need to be super lipophilic. So carbons alone don't get you past the blood-brain barrier. You need to have certain functional groups that allow you to increase the lipophilicity of the drug, but still maintain certain functional groups. Because remember, fluoxetine still needs to fit in a certain receptor or an enzyme or a region of the neuron. So we can't just come up with any random structure that has lots of carbons on it. It still has to maintain a certain 3D shape. In order to make a drug more lipophilic, one of the key ways we can do this is with just regular old alkyl groups. So you add, methyl, ethyl, butyl, whatever it is. The bigger the chain, the more lipophilic. So if you add a decane chain, that's way more lipophilic than if you had a ethane chain. The other thing that you can add is phenyl groups. So benzene rings are perfect ways of adding a ton of lipophilicity without changing the 3D shape necessarily. There's also some ideas about pi stacking and different stuff like that, but we're not going to focus on it. Likewise, halogens, very, very, very good, with fluorine being much other way. Iodine is more lipophilic than bromine, which is more lipophilic than chlorine, which is better than fluorine. And then finally is esters, which, if you remember, is where you have this carbon. Exactly, right. And we'll talk about that in a second. And this oxygen is branched onto a R group. The reason why esters are considered lipophilic is because they easily convert, once they enter into the body, into carboxylic acids. So the ester has a good lipophilicity, but it's easy to convert it to the carboxylic acid, which is more polar. So in other words, we create drugs that have esters in order to get them into the body, expecting them to blow apart into a carboxylic acid later on. That's the purpose of an ester. So what does this all mean? Essentially, what it is that we are going to be counting it, unlike the hydrophilic groups, which account for a number of carbons. Obviously, carbons are carbons, but halogens don't necessarily increase the lipophilicity by a certain number of carbons. They don't really work out that way. So all we can really say is that the more halogens you have, the more lipophilic you are. So looking at fluoxetine, we can say that this nitrogen would balance 5 to 6 carbons, so one of these benzene rings. And this oxygen would balance 2 to 3 carbons, so maybe, this chain here. But we have way more lipophilicity going on. So this drug is highly lipophilic, but terrible at dissolving, right? A lot of this drug is going to be trapped as as the tablet. And so this is why fluoxetine it requires a oh my God, what's it called? Counter ion. So you'll often see it needing I think they formulate it with sodium now. Fluoxetine sodium. Let me go to the package insert. Hydrochloride. So they pair it with a salt to help it with its dissolution, is essentially what's going on. So what does this mean on the exam? On the exam, he will give you 2 drugs. So let's say you have, oops, that's kind of it. Oh, let's go with this one. And let's get diazepam. So here we have 2 drugs. This is clonazepam. And here we have diazepam, which are 2 benzodiazepines. And so the question would be, which is more lipophilic? Which one is more lipophilic?
Would it be clonazepam?
Let's see. So what is the same and what's different? So in clonazepam, we have this benzene ring. In fact, we have the benzodiazepine ring. So this is the same in both structures. In clonazepam, however, we have this nitro group and we have this NH group. Whereas in diazepam, we have a chlorine and we have a methyl group here. Likewise, in clonazepam, we have an extra chlorine. So in terms of which is more lipophilic, let's look at very strong polar groups. So we know that polar groups are hydrophilic, which means that they do not like going through the membrane. So which one has OH, NH, and SH bonds? Clonazepam. So this drug has a much stronger polar group, and it has a nitrogen, right? Which we know is also weakly polar. Compare that with diazepam, where do we have an NH bond? No, this is a methyl group. So here, what we've done is we've added this methyl group in order to increase the lipophilicity. Same thing here. We swapped out the nitro group for the chlorine in order to increase the lipophilicity. You could argue that, you know, the fact that the chlorine is here versus here might cancel them out. You know, if that's how it works in your brain to kind of think about it, that's totally fine. But even here, we can say that here are two polar groups. We have no polar groups here. So who is more lipophilic? Diazepam. Does this make sense how we kind of talked about this? Kind of, sort of.
So
Okay.
diazepam is diazepam is more lipophilic because it has it's more weakly polar.
It is more lipophilic because it is less polar.
Yes, yeah, okay. Yeah. Okay. Yeah, okay, got it. Thank you.
No problem. Come on. Is this too small or can you guys see this?
Can you make it bigger?
I can do that.
Thank you.
No problem. Structure. All right. Here we have venlafaxine. And here we have duloxetine. And same question. Who is more lipophilic? Less polar is lipophilic. Yes. Yep. Okay. No problem. You can ask it once we go through this problem. So which is more lipophilic?
Duloxetine?
Venlafaxine, it's a toss-up, right? So here we have in venlafaxine, we have this OH bond. So this is very polar, 5 to 6 carbons. We have a nitrogen, which would be 2 to 3 carbons. And we have an oxygen, which is also 2 to 3 carbons. Compare this with duloxetine, and we have the same thing. We have an NH bond, which is very polar, 5 to 6 carbons. We have this oxygen, 2 to 3 carbons, and the sulfur, 2 to 3 carbons. So which is better? Neither one. So this is something I want to remind you guys that we don't only count heteroatoms. We also count carbons, right? So we have 1, 2, 3, 4, 4, this would be 10, 16, 17. And here we have 1, 2, 3, 4. 1, 2, 3, 4. This would be 8. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 18. So if both of them are solubilizing the same number of carbons, which one would technically be more lipophilic? The one with more carbons. So there's always two parts that you have to look at. You have to look at the number of polar atoms, but also the number of carbons. Here, I really should have picked one that had more atoms in it, more carbons, just so that way we had a bigger difference to compare. That's my bad. but hopefully the idea comes across. Does that make sense? So duloxetine would be more polar. Sorry, duloxetine would be more lipophilic because it has more carbons. Now, how would you count this if you had a fluorine on it? Having halogens would be the third thing to compare. So, maybe we have the same number of carbons, 17 and 17, but this one has a fluorine, then you would go with duloxetine. Or if it had, one fluorine versus two fluorines, go with the more halogens. Does that make sense? So the things that we're checking is the polarity, then the number of carbons, and then number of halogens. Are these? Yes. Yep. Is this a hard and fast rule? Not at all. This is more, he will give much clearer examples than this one. I just pulled two drugs off the top of my head and I can't believe that they're so close, but hopefully this illustrates the point. What was your question about fluoxetine as well?
Oh yeah, I was gonna ask, you said, what did you say? Oh yeah, you said it was super lipophilic, so that it won't absorb, or did I hear you wrong?
I don't remember how I said it, but if the more lipophilic you are, the better you are at absorbing.
Okay, that's what I thought, but I got confused, so I must have misheard you.
The more lipophilic you are, the worse you are at dissolving. Because you're not going to dissolve into the stomach acid or the water or whatever. But I can't remember what I said. But
And then for the esters, how is it that it's easily, like, it can easily become more polar compared to like ethers, or are those like, I mean, I know they're two completely different.
We'll talk about this when we get to metabolism. I think will
Okay.
help. That will clear up what's going on here. Technically, I shouldn't have brought it up because that's really metabolism, but
Oh, thank you.
my bad. No problem. Any other questions about absorption? All right. One of the big properties of drugs, especially when we talk about absorption, is charge. And the way that we modify charge is by looking at acid-base chemistry. If you remember all the way back from Gen Chem, we have this general formula where we have an acid plus a base, and the acid donates the proton to the base, and then it can go back and forth, back and forth, back and forth. Now, there are, in general, when we talk about drugs, we don't have an acid and a base molecule. Back in Gen Chem and organic chemistry, we did have two separate molecules that we were talking about. But when we talk about drug chemistry, what we have to go with is stomach acid, H+, plus drug gives us the protonated form of the drug. So once again, we have stomach acid plus the unprotonated drug combine to create the protonated drug. When we talk about absorption depends on the lack of polarity. Right? What do we mean by that? What we mean is we just learned that if you have something like an OH bond, we just learned that this is super polar. The reason for that is because we have a very strong partial negative charge on the oxygen and a very strong partial positive charge on the hydrogen. So the polar part of this is that we have a negative and a positive. The other way that you can have a very, very polar group is by having a full negative charge. So if you have a very polar group like OH, NH, or SH bonds, or if you have a full charge, are you going to absorb? Not at all. You are very bad at absorbing. Terrible absorption. What we find is that there are certain functional groups that, depending on the acidity in the body, so the stomach, the intestine, wherever it is, we get different absorption. And the reason for that is because the charge of the group changes. So let's take a look.
So both configuration have bad absorption.
Right. Yep.
And that's because of the electrons, right?
Correct. So either because you have such a strong negative and positive, or because you have a full charge.
Okay. Thank you.
So let's say that you have this drug in your body. We know that this functional group is called a carboxylic acid. And if you weren't aware, a carboxylic acid is an acid. And so one of the things that can happen is that depending on what kind of solution it is in, so, if you dissolve it in some water or you dissolve it in the stomach, it dissociates into its conjugate base, which this is a carboxylate. So we have a carboxylic acid or a carboxylate. In other words, we have our acid and our conjugate base. Of our two forms of our drug, which one is going to absorb better? Or in other words, of our two forms of our drug, which one is less polar?
The conjugate base?
Less polar.
Oh.
So very, very polar has a negative charge of one of these strong OH, NH, or SH groups. So if we don't want any polar at all, which is better, neutral charge or negative charge?
Neutral.
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 Are either one of these good for absorption? No, right? We know OH bonds, no bueno. But of the two of them, which one is preferred, or which one would have an easier time absorbing? The neutral charge. So the point I'm trying to talk about here is that in terms of absorption depends on the lack of polarity, which we talked about up above, and absorption loves neutral molecules. This is the key. So if you had to tattoo one thing on your hand for the exam, and then they yell at you because you're not allowed to have anything with you, is that absorption loves neutral things. The reason is because of the two forms, the neutral or the ionized form, even though it's an acid, yeah, the fact that it's an acid has nothing to do with absorption. Absolutely nothing. It's crazy, right? So let's take this and let's put it into practice. We have ibuprofen. I think this is ibuprofen. I can't remember. And we're going to put ibuprofen in the stomach. So the question that you would encounter is ibuprofen ionized, which is a fun way of saying charged, at a pH of 1.2. So it's in the stomach. And what they'll give you is they'll say it has a pKa of, let's say 3.7. The question becomes, how do we approach this problem? And I'm going to show you the setup that will work 100% of the time, no matter what functional group you're talking about. If we have a pKa, this pKa is describing 3.7 is the acidity of the drug. A pKa will always talk about a structure. And so when we look at the pKa of ibuprofen, the A tells us that we're talking about an acid. So looking at the two different forms of ibuprofen, we have this unprotonated form on the right, and we have a protonated form, sorry, unprotonated on the left, protonated on the right. Remember that the job of an acid is to donate it to something else. So is the unprotonated form or the protonated form the acid? Which one is the acid?
Wait, so you said the job of the acid is to give the
So acids have a bonded proton ready to donate.
yeah, then wouldn't it be the protonated then? Since it,
Does this structure have a hydrogen ready to donate?
yeah.
No, it's already left. He's gone. He's off on vacation. Remember, bonded,
mm,
right?
yeah.
So our hydrogen has already left for vacation. So which one is the acid? The one on the left. Which means that this is the conjugate base, right?
Yeah, yeah, I see, yeah.
Sweet. So here's my question for you. Does the acidity constant, the acid constant, does that, is this number 3.7 describing the unprotonated structure or the protonated structure? Is the acid constant describing the unprotonated or the protonated?
Protonated?
Which one's the acid?
The one on the left, the one with the OH.
Right. So this would be this would be described by a pKa, right?
Yeah.
Because it's the acid. We could describe this with pKb, even though we don't really ever talk about pKb. But which structure is being talked about with pKa is the acid over here. Does that make sense? How we found which structure is being talked about?
Yeah.
Okay, sweet.
And that rule with the acid bonded, with acids have a bonded H ready to donate, that applies to.
Everything. Always true.
Oh, gotcha. Okay. Thank you.
No problem. My secret for you is that pH will always describe that free H+ ion. So the pH is being described over here. And what this is specifically is the acidity of the solution. So in this case, it's the stomach, but we could be talking about the acidity of the lung, maybe of the blood, could be the intestines. But what's important here, and that we can always check to make sure that we've done this right, is that our pKa is on the opposite side of our pH. And the reason for that is because Mother Nature will always choose the higher number. And the reason for this is because it's a weaker acid. So which value will Mother Nature prefer? Well, it's going to prefer having this pKa exist rather than this pH. So if we were to drop ibuprofen into the stomach, what form are we going to find it in? The unprotonated form.
Can you repeat that? Sorry.
Yes, of course. Mother Nature will always choose the weaker acid, which is, if remember that the strongest acids are the most negative number. So the higher the number, the weaker the acid. And so because Mother Nature will always choose the weaker acid, we choose the arrow that points towards the higher number, which means that if we were to have ibuprofen at a pH of 1.2, the structure that we would find it in is this one off to the left. So in terms of our question, is ibuprofen charged at a pH of 1.2? The answer would be no, because it's the unprotonated, uncharged form. Does that make sense? Should we do another practice?
Yes.
All right, let's talk about that. If you go through the packet, he talks about there are 4 acid functional groups and there are 4 basic functional groups. But the principles that we're going to talk about are exactly the same. What's your question? What's your question? When would the answer be yes? I'm glad you asked. We're going to take a look at that. For drug X, what would the charge be at pH of 7.3? So around blood temperature, blood pH. So let's say that we have I want to do sulfonamide. Is this am I crazy? I just want to make sure I'm talking about do. I can't find it. I don't want to give you the wrong information, so I'm gonna swap this out for a image. We can do a phenol. We'll do that. We'll pop this off. And we will put an OH here. So you have this structure of a drug. And what I'm going to tell you is that you have a pKa for this drug of, let's say, 5.6, making it up. So this is all the information you're given for this question. And what we can identify is that this is the functional group phenol, which as you guys create your flashcards, you will identify this as one of the acidic functional groups. What that means is that when we look at the other potential structure, is that this hydrogen is the one that gets popped off. Because we know that acids have a bonded hydrogen ready to donate. So what is the other structure going to be? It's going to be the same structure, except that that hydrogen has popped off and gone on holiday. Does that make sense so far? Any questions about how we found that? All right. So,
Oh, sorry.
no, what's your question?
Yeah, just like you said earlier, so the pH would represent the one on the right and the pKa would be the one on the left.
Correct. Yep. The reason why the hydrogen popped off is because acids donate a hydrogen. That is the function of an acid. So what we are essentially looking at here is the comparison of the drug, so the pKa, versus the pH. So the reason why it popped off is because it's an acid, and so that way we can have this H+ to be able to compare across. Does that make sense?
Yes, it does. Thank you.
No problem. All right. Okay, great. So we follow the rule. Mother Nature will always choose the higher number, which is the weaker acid. So which is the weaker acid, the drug or the solution? Which would be weaker?
The solution?
So,
I would agree. 7.3 is a higher number than 5.6. So Mother Nature will, in this case, choose the solution, which means what would the charge be on drug X at a pH of 7.3? Well, the only charge there is negative.
Oh, got it. All right, bad.
Another question I could ask is, at a pH of 7.3, would drug X absorb easily?
Yes, because it's no, because it's not as polar as the one on the right. Because like just like you said earlier, you said Mother Nature would prefer the neutral rather than the charged, right?
Right. So the best kinds of drugs for absorption are neutral, right? But here at a pH of 7.3, is this going to easily absorb? No, because it's charged. Does that make sense?
Yes.
Sweet. So just to explain this once again, is that for Mother Nature, we'll always choose the higher number. So in this case, she's going to choose 7.3, which means that the structure of drug X will be this charged molecule. So for the first question, what would the charge be at 7.3? Negative. And then at a pH of 7.3, would drug X absorb easily? No, it would not, because it is charged. And we know that absorption loves neutral molecules. How do we feel about this? Good? Somewhat good?
Somewhat good.
Good.
Okay. Better than class is the, the way I like to put it.
Yeah, definitely.
Okay. All right. Then I'm doing my job. All right. We just talked about acidic functional groups. Let's take a look at basic real quick. In the function of basic groups. So an acid's job, as we talked about up above, is to have an extra hydrogen and it gets rid of it. So in other words, we have a drug that has this hydrogen and it will get rid of the hydrogen to the solution. A basic functional group is the reverse of this. So a basic functional group is going to wait for the solution to donate a proton to it. The functional groups that are most able, the functional groups that you'll find in drugs that act like bases are amines, pyridine, and aniline. Amines, pyridine, and aniline. If it is not an amine, pyridine, or aniline, it does not act as a basic functional group. Does that mean it's acidic? Not necessarily. And we're going to look at, there are tons and tons of neutral nitrogen-containing functional groups. But what I don't want you to fall under the assumption is anytime that you see a nitrogen, it's suddenly basic. Only these three types. So the way that we're going to use these is very, very, very similar to how we would talk about acidic functional groups. So let's say that we have drug Y. Will drug Y be charged at a pH of 4.5? And let's say, for instance, I give you that it has a pKb of 3. So here is our drug. And what I want you to know is that the conjugate structure for amine, pyridine, aniline is the same structure plus that hydrogen that gets donated. Remember that for basic functional groups, we have that proton plus the drug creates that protonated form of the drug. So does this nitrogen over here have a hydrogen? No. So what we can add is the H plus. So now it's mimicking this left-hand side of the equation. And so this H plus will get donated to the structure. And so we have our unprotonated form and our protonated form. Does this make sense how we got here? So remember that these structures, the basic functional groups, do they have a hydrogen to begin with? Does pyridine have a hydrogen? No. That's why the H plus is on this side, because it gets added to the pyridine to create this protonated form. So pyridine naturally doesn't have a hydrogen in the same way that a carboxylic acid naturally does. That's why they're opposites of each other. So we know, right, that what do we always say? pH will always describe the H plus ion. So we put our pH over here, and we say that this is 4.5, which means that where are we going to put pKb? Well, we can't put it on the same side, so it must go on the opposite side. Does that make sense? Is anybody confused about how we place these? Okay.
So,
Nope. What's your question?
I was just gonna say, so now it would kind of be similar to the process we did earlier. So the PKB would represent the base, like not the base, but like the basic, like,
So this is the problem, essentially. Remember that we said that pH is about pH describes the acidity of the solution, right? Here, I wrote it here. Acidity of the solution.
Yeah.
So how can we compare the acidity of the solution with the basicity of the drug. These are two opposite properties. So what I want to show you, and I don't remember if this was on the exam, I think it was just something he talked about, but it's kind of weird. I don't remember how it plays in, but I'm going to show you just to cover all our bases, is that pKa plus pKb equals 14. So we have pKb, so we know that the pKa plus 3 equals 14, which means that the pKa of this molecule is around 11. So can we use pKb to go with our Mother Nature rule? No. We can, however, use its pKa, which would be 11. So on the exam, if you're ever given a pKb, immediately convert it to pKa, because pH will always describe acidity. It will never describe basicity. Does that make sense? Anyone have questions on that? All right. So now that we're talking about an acid and we're talking about an acid, we can say Mother Nature will always choose the weaker acid, which means the higher number. So Mother Nature will choose the structure on the right. So will drug Y be charged at a pH of 4.5? Yes. Does this make sense? Any questions about this?
Yeah, I had a question.
Mhm.
So how did we know again that the pH would be on the unprotonated side?
How we knew is, so pH will always follow wherever we put the H plus. And we knew to put the H plus over here because the basic functional groups lack that hydrogen. And so we need to combine the hydrogen with the nitrogen in order to get this protonated form. So the short answer is it followed wherever we put the H plus.
Oh, okay. And then we put the pKb on the protonated side and then just converted the pKb to pKa and then used that to answer the question.
Exactly. Yep.
Okay.
Now, what's important is that the pKa is always on the opposite side to the pH. So if you're ever doing this problem and you're trying to put both on the same side, you're doing it wrong. So that this is a way for us to check that we're talking about it the correct way. All right. We started a little bit late, so we're going a little bit over when it should end, but I want to talk about Henderson Hasselbalch because he went over it in class today and I heard he did not do a very good job. So I want to talk about it. Percent ionization. I love talking about acid base. It's one of my favorite lessons to teach in Orgo, purely because nobody can explain it. And I feel like I can do a little bit better job than like Poulos or Shia or Mahana. All right. Remember that when we talk about any structure, the pKa is the acidity of that structure. And what we can say about pKa is that it is specific to that functional group. And where that pKa is, how the charge of the structure changes is dependent on pH. So what do I mean by that? What I mean is that if you have a pKa of 3.2, so here we are talking about an acid. And if we look at the number line of 0 all the way to 14, we have our drug here at 3.2. Maybe it's a little bit further up. pKa. What I will show you is the quick and dirty way of figuring out if a molecule is going to be charged if you have the pH available. So instead of drawing out the structure, what we can do is we can say, okay, let's say I have an acidic functional group. So maybe we have a carboxylic acid, and I know that the generic formula of an acid is this guy. Without even knowing the structure of the drug, I can figure out if it's going to be charged or not. Because what did we say earlier? If, let's say that we are working with this functional group at a pH of 6.8, we know that pH is always describing H+. Which means, where are we going to put this pKa? On the other side. So at a pH of 6.8, which one, what form of the drug is going to be preferred? The neutral form or the charged form? Which one is going to be preferred? Charged, right? Mother Nature will always, always, always choose the higher number, which in this case is 6.8. So as it turns out, anything to the right of this acid molecule will be charged. Because as long as you pick any number greater than 3.2, if I swap this out and I chose 3.3, Mother Nature is still going to choose 3.3 and give us the charged form. Which means anything below 3.2 will be neutral. Is everyone with me so far? Do we get how we figured this out?
Yes.
And that's the pH, right?
The 3.3 or the
Yeah, like the charged and the neutral. Or
yes, it's depending. No, like if you picked any pH in this region, it would be neutral structure. Yeah. All right. So the question becomes, let's say I'm asking the question, at a pH of 4.2, how does he phrase it? What percentage will be, what percentage of molecules will be ionized? Which once again is just a fun way of saying charged. Well, we drew our little diagram here, and we can say that 4.2 is right here, which means that it falls into the charged region. So just conceptually, before we even get into any of the math, do we expect there to be more charged molecules or less charged molecules?
More.
More, right? Because we're moving further into the charged region. And so this is where we get that rule of 10. Essentially, what the rule of 10 says is that if you have a molecule at a pH equal to its pKa, so if we had the pH at 3.2, then we'd have 10 ionized and ionized on top. Am I crazy? Acidic form, basic form. Yes. And 10 unionized, which again, ionized is a fancy term for charged. If we wanted to take a percentage of this, we would say that we have 10 ionized out of 20 total molecules, right? Because we have 10 ionized, 10 unionized, which means 50%. So when the pKa is equal to the pH, then we have 50% charged, 50% uncharged or unionized. What we say and what the rule is that for every step in the direction you're going, you change the balance of those molecules. So what I mean by that is we know conceptually that when I move towards 4.2, I know that the number of ionized molecules I have should increase. And what we find is that that increase is as if you did 10 ionized over 1 unionized. So ratio of 10 to 1. What this means is that at a pH of 4.2, 10 out of every 11 molecules is going to be ionized. Which, if you do, 10 divided by 11, you get 0.90, which is around 90%. If you were to hop another space and go to 5.2, what we would find is that we would have a ratio of 100 ionized to every 1 unionized. Which would mean that we have 100 ionized for every 101 molecules, which is around 0.99 or 99%. Does this make sense so far, how we're getting these numbers? How we're talking about this ratio?
So it just increases proportionally pretty much.
Exactly.
6.2, it would be 1,000 to 1,001.
Right. Yep. 1,000 over 1. Yep. Yep. In the same way that if we went to 2.2, it would be 1 ionized for every 10 unionized. So the opposite of 4.2. So at a pH of 4.2, to answer a question, what percent of molecules will be charged? 90%. That's how we found that number. So let's look at the example he gives in the packet. Yep, that might be too small. And if anyone has any questions, please stop me. I can go over it again. I really don't mind. This stuff is confusing. The words are very similar to each other. I get it. So I really don't mind. All right. Phenobarbital has a pKa of 7.7. At a pH of 6, it is expected to be oh, we didn't talk about salts yet, did we? No. That's okay. So what I will tell you is here we have an acidic drug, phenobarbital. So we know that acidic drugs are described by this formula. And so we know that pH will always follow wherever we put that H plus. And so we can put the pKa on the opposite side. So at a pH of 6, is Mother Nature going to choose the neutral or the charged form? Is it going to choose the left or the right? I would agree. Left side, right? Mother Nature will always choose the higher number, will choose the weaker acid. So in this case, 7.7. So when we construct our number line, zero, 14, 7.7 in the middle. Is going towards 6. Is this going to be the charged domain or the neutral domain, the charge domain. How do I know that? Because as I get closer to 6, this is going to become more and more charged, right? I'm following no. Did I just say that backwards? Yes, I did say it backwards. Right? Because at 6, it will be neutral. Yes. My bad. Remember what we just described, right? That here is the drug. The drug is existing right at 6. And so at a pH of 6, what form did we just say it was going to take? The neutral form, right? So what this setup is explaining is that whichever side of your pKa points to that pH will be the result of the arrow you chose. So in other words, pointing towards pH of 6, we should have neutral molecules. Whereas pointing away from a pH of 6, we would have charged molecules. Any questions about that? Okay. Like I said, if I'm being confusing or if I'm not making sense, please let me know. So we know that as we go towards 6, we should be more unionized. So what we can set up is a ratio and say that at 6.6, we do this in a different color. We would expect to have 1 ion for every 10 unionized. And at a pH of 5.6, we would expect 1 ion for every 100 unionized molecules. So what this would mean is that we would have 10% ionized for 90% unionized versus 1% ionized for every 99% unionized. So for a pH of 6, this would mean, and how to interpret this, is that it would be 1 to 10% charged or 90 to 99% uncharged. Let's back up. No worries. So, oh, I don't know why I put 7.6. It should be 7.7. That's probably the first thing that's confusing is me just choosing the wrong numbers. We know that as we move towards this pH, as we move towards the left, we get a more neutral molecule. Remember that neutral is the same thing as unionized, non-ionized, uncharged. They all describe the same molecule. And so as we move towards this structure, what we find is that the number of molecules that would be uncharged or unionized increases. So at 1 pH jump, it would be 1/10. At a second pH jump, it would be 1/100. And if we went to 4.7, it would be 1/1000. We can, instead of writing it as 1/10 or 1/100, we can write this in terms of percentages. So 1 divided by 11, 1 ion divided by 11 total molecules is 10%. We can do the same to get 90%. And then at 5.7, we have 1/101. So 1% versus 99%. So what this has done is it's given us a range and said that at this pH of 6, which falls in between these two values, 5.7 and 6.7, between 1 and 10% will be ionized, and between 90 and 99% will be unionized. Does this make sense? Are we? Okay. Great. Now that we figured this out, we can answer our question and say, will phenobarbital be 99 to 100% ionized? No, it should only be 1 to 10%. Will it be 90 to 100% non-ionized? Yeah, that is true. 50 to 90% ionized? Nope, only 1 to 10%. Only 1 to 10%. And this is supposed to be 90 to 99% or 100%. So our answer here is B. How do we feel? Thumbs up, thumbs in the middle, terrible. How do we feel?
Wait,
Middle?
so the answer is B?
B. Yep.
Because it's between 90% to 99% unionized.
Yes. Yeah. So I guess he rounded up the 99% to 100. If that, I don't know why he did, because usually he doesn't.
And so on the exam, if we come across a question like that, we should set it up, do the bar, and then just go through the process of unionized, the percentage of ionized, unionized.
Yes. Yep. What I will say is that this gets much easier the more you practice it. So we still have a good amount of time before the exam on the 28th, I think, right? I can't remember. Whatever. So we'll have extra time after the PCOL exam to really go through this and really cement it. It gets easier. I promise you, it gets much easier. This is probably the worst part of this exam, is talking about acid base. My favorite part is metabolism, but it gets easier, I promise. All right. Great, 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 great. Uh, couple of things for the exam next week. Please, 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 please know your GPCR mechanisms. So, how the second messengers interact, how that process happens. You should know it by heart. You should be able to write it in your sleep. If I walk up to you on the street and say, here's a piece of paper, write out the, GS GPCR, you should be able to draw me the entire thing. Did you guys have PCOL today? I can't remember.
Yeah, we did.
Yep. Okay. Make sure you understand the definitions of affinity, potency, efficacy, how that gets talked about on a graph. Very, very important. Get that locked down during the weekend, because you don't want to have to be thinking about that next week, because there's a little bit more confusing stuff at the end of the first packet. Let me just pull it up real quick. Yes, the pharmacogenomic stuff. So please, 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 have the pages 1 through 18 locked down as soon as possible, and then really spend the weekend studying pages 19 through probably 26, because the pharmacogenomic stuff can be a little bit confusing for people. And everything in that regard. Any questions for me? All right. Well, I hope you guys have a great rest of your week. If you have any questions while you're studying, please let me know. I realized that I didn't put a way to contact me here, so I will do that now. Oop. Great. All right. I will see you all later in the week. Later
Thank
next
you.
week.